In the previous videos of our hydraulic calculation series, we explored key concepts such as flow rate, pressure, pressure loss, K factor, density, and design area. In this video, we'll see how to apply those concepts in our first full hydraulic calculation, connecting theory to practice, step by step. Let's assume we're designing a wet pipe fire sprinkler system for a room measuring 100 by 52 feet. This space falls under Ordinary Hazard Group 1 occupancy. We'll be using upright standard spray sprinklers with a K factor of 5.6 and standard response thermal sensitivity. The piping material will be black steel Schedule 40. In the first step, we locate the sprinklers and define the piping layout. In this arrangement, the sprinklers are uniformly spaced, with 13 feet between heads along each branch line and 10 feet between branch lines. As a result, each sprinkler covers an area of 130 square feet. Based on the occupancy hazard classification, which is Ordinary Hazard Group 1, NFPA 13 requires a minimum design density of 0.15 gallons per minute per square foot and a design area of 1,500 square feet for hydraulic calculations. The total number of sprinklers within the design area will be 12, with 4 sprinklers located on the most remote branch line. Based on this configuration, the design area forms a rectangular shape, as illustrated in the figure. At this stage, we begin by estimating the pipe sizes throughout the system. Then, we start our hydraulic calculations from the most remote sprinkler and work our way back through the piping network toward the water supply or a point where pressure and flow rate are known. If the calculated system demand based on our initial pipe size assumptions doesn't meet the requirements, we'll revise the pipe sizes accordingly. For our initial pipe size assumptions, let's use the following guideline. Pipes feeding a single sprinkler will be 1 inch in diameter. Pipes feeding up to 4 sprinklers will be 1¼ inches. Pipes feeding more than 4 sprinklers will be sized at 2 inches. Additionally, we'll assume a 4-inch diameter for the riser. Let's take a look at the 3D model of our sprinkler system. As shown, the sprinklers are installed directly on the fittings. The branch line sizes follow our initial assumptions, and the cross main is sized at 2 inches. On the 4-inch riser, we've included a flow switch, a wet alarm, and a butterfly valve. We're assuming this sprinkler system is connected to a private fire service main and that the flow rate and pressure at the lower flange are known. For hydraulic calculations, we divide the piping network into sections or segments. Each section is defined by a start node and an end node. A node is placed at the starting and ending points of the hydraulic calculation, as well as at any location where there's a change in flow rate, C factor, or pipe size. In some cases, we also add extra nodes to make the system easier to review or analyze. As mentioned earlier, we begin our hydraulic calculations from the most remote sprinkler and work our way back through the piping network toward the water supply or to a point where the pressure and flow rate are known. Therefore, the first node is placed at the most remote sprinkler since it marks the starting point of the hydraulic calculation. We'll label the first node as 101. On the way back toward the end point of the system, the second node is placed at the adjacent sprinkler. This sprinkler is located within the design area, which means it contributes to the system's flow demand. Additionally, the pipe size changes at this point, from 1 inch to 1¼ inches, making it a logical place to assign a node. We'll label this as node 102. The section of the system between node 101 and node 102 is referred to as the first section. The next node, labeled 103, is placed at the third sprinkler. Although there's no change in pipe size or C factor at this point, the flow rate changes since this sprinkler is still located within the design area. Similar to node 103, the fourth sprinkler will be labeled as node 104. The next node is placed at the intersection of the branch line and the cross main where the pipe size changes. We'll designate this point as node 1. Continuing along the path toward the end point of the system, the intersection of the second branch line and the cross main becomes the next node. This is because a portion of the system's flow rate is discharged through the 4 sprinklers installed on that branch line. We'll label this intersection as node 2 and assign the sprinklers as nodes 105, 106, 107, and 108. The node numbering for the third branch line and its intersection with the cross main follows the same logic as the second branch line. Therefore, we'll label the nodes accordingly based on changes in flow rate and pipe configuration. As we continue toward the end point of the calculation, we reach the intersection of the fourth branch line and the cross main. Since the sprinklers on this branch line are outside the design area, we do not expect them to activate or discharge water. Additionally, there is no change in pipe size or C factor at this location. Therefore, there is no need to assign a node at this point. For the same reasons, there's no need to assign a node at any of the remaining intersections between the branch lines and the cross main. The next node is placed at the intersection of the cross main and the riser, where the pipe size increases to 4 inches. We'll label this point as node 4. The final node is placed at the flange, where we've assumed the flow rate and pressure are known. We'll label this point as the test node. Now that we've defined all the necessary nodes throughout the system, we're ready to begin calculating the flow rate and pressure at each node. We begin our calculation from node 101. As reviewed earlier, the coverage area of the sprinkler is 130 square feet, and the required density is 0.15 gallons per minute per square foot. To find the flow rate, we simply multiply these two values. So the flow rate at node 101 is 19.5 gallons per minute. The K factor of the sprinkler is 5.6. To calculate the required pressure, we divide the flow rate by the K factor and then square the result. So the required pressure at the most remote sprinkler is 12.1 psi. Now that we've calculated the flow rate and pressure at node 101, we can move on to the next node and determine the flow and pressure at node 102. Since we already know the pressure at node 101, we can calculate the pressure loss along section 1 to determine the pressure at node 102. The pressure loss in section 1 consists of both major and minor losses. In this section, we have one elbow and one T fitting. However, we can ignore the minor loss in the elbow as NFPA 13 permits, excluding fittings where sprinklers are directly installed on them. Additionally, we can ignore the minor loss in the T, as the standards permit excluding T's or crosses that do not cause a change in flow direction. In our example, the water does not experience any change in direction as it passes through the T fitting. Therefore, we can ignore the minor loss in the T in accordance with standard guidelines. As a result, the only pressure loss in section 1 is due to friction, which we calculate using the 𝐓𝐨𝐻𝐸 formula. Since this formula provides the pressure loss per foot of pipe, we determine the total pressure loss by multiplying that value by the length of the pipe in section 1. In the 𝐓𝐶𝐸 formula, the variable Q represents the flow rate passing through the pipe in section 1, which ultimately discharges from sprinkler 101. In the previous step, we calculated this flow rate as 19.5 gallons per minute. Since the pipes are black steel and the sprinkler system is a wet pipe system, according to Table 282481, the C factor shall be taken as 120. In the 𝐓𝐶𝐸 formula, D represents the internal diameter of the pipe. For Schedule 40 steel pipes, this value should be taken from Table A1632. For a 1-inch pipe, the internal diameter is 1.049 inches. Based on the sprinkler layout, the length of the pipe in section 1 is 13 feet. Applying the data and performing the calculations, the pressure loss in the pipe between sprinklers 101 and 102 comes out to 1.6 psi. Now that we've determined the pressure loss in section 1 along with the pressure at node 101, it's straightforward to calculate the pressure at node 102 by adding these two values. The result is 13.7 psi. To calculate the flow rate of sprinkler 102, we simply apply the equation Q equals K times the square root of P. Since we already know both the K factor and the pressure, it's easy to find the flow rate. The result is 20.7 gallons per minute. The process of finding the flow rate and pressure at sprinkler 103 is very similar to the previous step, with just two key differences. The first is the value of Q in the 𝐏𝐸𝐸𝐬 formula. We must remember that the flow rate in this section is discharged from sprinklers 101 and 102. Therefore, the combined flow rate from both sprinklers must be used in the 𝐏𝐸𝐸𝐬𝐬 formula. Sometimes this detail is overlooked, and only the flow from sprinkler 102 is used, which can lead to a significant error in the pressure loss calculation. The second difference is a change in pipe size. For this section, we're using a 1 1/4 inch Schedule 40 steel pipe, so we must apply its internal diameter, which is 1.38 inches, as specified in Table A 16.3.2. Since the pipes in our example are black steel and the system is a wet pipe, the C factor for this section and for the remainder of our calculations will be 120 as specified by the standard. The length of the pipe in this section is 13 feet as indicated in the layout. The total pressure loss in this section calculates to 1.6 psi. Interestingly, although the flow rate here is more than twice that of section 1, the pressure loss per foot remains almost the same. This highlights the impact of increasing the pipe size and the influence of the exponent 4.87 in the 𝐏𝐸𝐸𝐬𝐬𝐬 formula, which significantly reduces friction loss as diameter increases. With the pressure loss in section 2 and the known pressure at node 102, we can now calculate the pressure at node 103, which comes out to 15.3 psi. Using the pressure at this node and the known K factor of the sprinkler, we calculate the flow rate of sprinkler 103 to be 21.9 gallons per minute. We'll follow the same procedure as in section 2. This time, the only change in the 𝐏𝐸𝐸𝐬𝐬𝐬 formula is the flow rate, which now equals the total flow from sprinklers 101, 102, and 103. The pressure at node 104 is calculated to be 18.9 psi and the corresponding flow rate is 24.3 gallons per minute. It's worth noting that although the sprinkler is required to discharge only 19.5 gallons per minute based on its coverage area and design density, as we move closer to the water source, the pressure increases, allowing the sprinkler to discharge more water. In this case, the flow rate at sprinkler 104 is approximately 25% higher than the minimum required. This phenomenon is known as overage, a built-in safety margin in hydraulic calculations that enhances system reliability during real-world operation. As mentioned earlier, node 1 is the intersection between the branch line and the cross main. There's no sprinkler at this point, so the system flow remains unchanged. However, there is a T-fitting that changes the flow direction, and we need to account for its minor loss by applying an equivalent length in our calculations. To determine the pressure loss in section 4, located between nodes 104 and 1, we use the total flow rate from all 4 sprinklers as the value of Q in the 𝐏𝐸𝐸𝐬𝐬𝐬𝐸 formula. The length of the pipe in this section is 4.5 feet. Since the sprinklers are spaced uniformly, The distance from sprinkler 104 to the south wall is half the sprinkler spacing, which equals 6.5 feet. Assuming the cross main is positioned 2 feet from the south wall, the resulting pipe length is 4.5 feet. According to Table 28-2311, the equivalent length of a T-fitting in 1 1/4 inch pipe size is 6 feet. This value will be added to the actual pipe length to account for minor losses in our pressure loss calculation. Using this data, the total pressure loss in Section 4 is calculated to be 5.4 psi. Therefore, the pressure at Node 1 will be 24.3 psi. As explained in the K-factor video, to simplify the next steps, we calculate the equivalent K-factor of the most remote branch line by dividing the total flow rate by the square root of the pressure at Node 1. This gives us a single representative K-factor for the entire branch line, making it easier to model this part of the system as one equivalent sprinkler. In Section 5, we only need to calculate the pressure loss. There's no change in flow rate through this segment. However, since the pipe size increases in this section, we must use the internal diameter of 2 inches in the 𝐏𝐸𝐻𝐸 formula. The length of the pipe in this section is 10 feet. Although there is a T-fitting, it does not change the flow direction, so we can ignore its minor loss and proceed with the actual pipe length in our pressure loss calculation. It's worth emphasizing again in Section 4, using 1 1/4 inch pipe, the pressure loss per foot was over 0.5 psi, but by increasing the pipe size to 2 inches in Section 5, the pressure loss per foot drops dramatically, down to just 0.07 psi. This clearly demonstrates the powerful effect of pipe diameter on friction loss, especially due to the exponent 4.87 in the 𝐏𝐸𝐻𝐸 formula. The pressure at Node 2 is calculated by adding the pressure at Node 1 to the pressure loss across Section 5. In this step, we need to determine the pressure at Node 3. To do that, we first calculate the flow rate through Section 6, which lies between Nodes 2 and 3. This section supplies both the first and the second branch lines. From previous steps, we know the flow rate of the first branch line is 86.4 gallons per minute. To calculate the flow rate of the second branch line, which includes sprinklers 105 to 108, we apply the concept of an equivalent K-factor. Since both branch lines are identical in terms of pipe size, pipe length, C-factor, sprinkler type, and number of sprinklers in the design area, we can use the same equivalent K-factor from the first branch line. By knowing the pressure at Node 2, we can now calculate the flow rate discharged from sprinklers 105 to 108. The equivalent K-factor is 17.5 and the pressure at Node 2 is 25 psi. Using the formula, the flow rate in this branch line calculates to 87.5 gallons per minute. Now, by adding the flow rates of the first and second branch lines, we determine the total flow through Section 6. With this value, we can calculate the pressure loss in Section 6 and subsequently the pressure at Node 3. In this step, we need to determine the flow rate and pressure at Node 4. Just like the previous step, we begin by calculating the flow rate of the third branch line. Since this branch line is identical to both previous ones in terms of pipe size, length, C-factor, sprinkler type, and number of sprinklers, we can confidently use the same equivalent K-factor. Using the pressure at Node 3, we apply the formula to determine the flow rate discharged from sprinklers 109 to 112. At this point, we've calculated the flow rate of all sprinklers within the design area of our system. Therefore, the total flow demand of the system is 265.8 gallons per minute. The length of the pipe in Section 7, located between Nodes 3 and 4, is 73 feet. To account for minor losses, we include the T-fitting at the intersection of the cross main and riser. The size of the T is taken as the size of the cross main, which is 2 inches. According to Table 28.2.3.1.1, the equivalent length of a 2-inch T is 10 feet. It's important to note that all other T-fittings at the intersections of branch lines and the cross main are ignored, since they do not change the flow direction and therefore do not contribute to minor loss. Based on the pressure at node 3 and the calculated pressure loss in section 7, the resulting pressure at node 4 is 75.2 pounds per square inch. In the final section of our piping network, located between node 4 and the test connection, there are a few important considerations to address. First, this segment includes components such as the flow switch, alarm check valve, and butterfly valve. We'll review how to account for their impact on pressure loss. Second, and for the first time in our hydraulic calculation, we encounter a change in elevation. Up to this point, all nodes were assumed to be at the same elevation, but now we must factor in elevation change, as it directly affects the pressure at the test connection. Let's begin by calculating the major and minor losses in this final section. As we know, major loss refers to the friction loss that occurs along the length of the pipe. Minor loss, on the other hand, results from local disturbances and energy dissipation caused by components such as valves and fittings. The flow rate in this section remains the same as the previous one, 265.8 gallons per minute, and the C factor is 120. The pipe size in this segment changes to 4 inches, so according to Table A 16.3.2, we use an internal diameter of 4.026 inches for our calculations. Additionally, we assume the pipe length to be 9 feet. According to Table 28.2.3.1.1, the equivalent length of a flow switch is 30 feet. It's important to note that in earlier editions of NFPA 13, we were allowed to ignore pressure losses through flow switches larger than 2 inches. However, in the 2025 edition, this exemption has been removed. We must now include the pressure loss of the flow switch regardless of pipe size. Since the equivalent length table in NFPA 13 does not include a value for the alarm check valve, the data must be sourced from the manufacturer's technical data sheet. For this calculation, we assume the equivalent length of the selected alarm check valve to be 21 feet. For the butterfly valve, we apply the value listed in the NFPA 13 table, which assigns an equivalent length of 12 feet. Now that we've gathered all the necessary data, we're ready to calculate both the major and minor losses in this section of pipe, which amount to 1.6 psi. As mentioned earlier, the start and end nodes in this section are not at the same elevation. If we assume an elevation change of 9 feet, the resulting pressure change is calculated by multiplying 0.433 by 9, which gives us 3.9 psi. This value must be added or subtracted depending on whether the elevation is rising or falling. If the end node of the section is lower than the starting point, we add the calculated pressure change. If the end node is higher, we subtract it. In our example, the end node is lower, so we add the 3.9 psi resulting from the elevation change. To calculate the pressure at node test, which also represents the pressure demand of our system, we simply add the pressure at node 4 to the pressure losses we've calculated in this final section. This gives us a total of 80.7 psi. We've now determined the flow and pressure demand of the system based on our initial pipe sizes. The next step is to compare the system's demand with the available flow and pressure from the private fire service main that we've assumed is feeding our system. From there, we can begin to optimize the system design to ensure both efficiency and compliance. This topic involves several important considerations and design strategies, so we'll explore them in a separate video dedicated to system optimization. Finally, even though all required parameters have been calculated, submission and approval by the authority having jurisdiction requires that these calculations be documented in the specific format defined by NFPA 13 as the detailed worksheet. In the next video, we will explain this format in detail and learn how to fill it out step by step.